Alright, so as we begin in this problem, we have an unknown compound and we have the formula of the unknown, which is right over here. Oh, let me change colors and show this. You guys may not see it, so I'm going to go ahead and rewrite it and tell you guys that this is going to be C10H12O. And I know in the assignment rubric, I would need to include the assigned number or letter that was given to me. And there was an assigned letter, which is right here, which is supposed to be L. So as we go ahead and move forward, I will go ahead and go to the next step and talk about the problems and talk about the spectrum. Alright, so moving on. So as we can see here, all of these are spectrums. The first one that we could see here, which is right here, is going to be the IR spectrum. And we also have the proton NMR, which is right here. And also, we also have the carbon-13, which will be the last one right here. And it's really important that all of these spectrums correspond to the same molecule. And as we move forward, we need to start with the infrared spectrum because I like to analyze that first so we could get an idea of the function. Alright, next thing, I also apologize because I'm using a different device right now. So moving on, for this recording I'll be describing the infrared spectrum. The main molecular formula, as we see up top, is the C10H12O, and its main functional group is a ketone attached to an aromatic ring. So now let's go through the key IR absorptions. First thing that I see here, that there's a carbon double bond to an oxygen with stretch, which would be a carbonyl group right here, carbonyl group. It has a strong sharp absorption around 1600, 1700. There's not really a number here that we could tell, but for around here, I want to say it's in between this 1700 and 1600. So it's in between there. Next, we need to focus on the CH stretches, which is around 2850 and 2850 and 2960. And the pink one, as we see right here, is right there next to the 3000, but right before it. So yeah, like I said, it's between 2850 and 2960. We observe the strong alkyl CH stretching bands, and also around 3000 to 3100. But this is very weak to medium peak from the aromatic, the CH stretching. But it's very weak in medium, so we could move on to the next one because it's weak. But the main focus about this IR as of right now is the ketone. The next major thing that we need to focus about is the carbon double bonded carbon stretching. The peaks in the region between 1600 and 1500 corresponds to the CH double bonded to a carbon stretch. Sorry, so it's a carbon double bonded to a carbon stretching in the aromatic ring. There are also additional, out of plane CH bending between, 700 to 800. Actually, I want to say it's between 700 to 900. I'm sorry. We'll go back. Yeah, it's 700 to 900, somewhere around there. It's out of plane though, so we could move past by that one. And the major thing here that I notice of this IR spectrum is that we do not have an OH stretch. We don't have a broad OH stretch around, 3300. So, in summary, the key indicators in the IR spectrum are a strong ketone, a carbon double bond to oxygen carbonyl group, stretch around, 1600 to 700, 1600 to 1700, and an aromatic carbon, CH and carbon double bond carbon stretches, and the alkyl, CH stretches from the branched group. And so, yeah, this is for the section of the infrared spectrum. And one more thing I want to point out, I also want to apologize for this. So the first spectrum that we were looking at is the infrared. So as previously, which is correct, that we are looking at the infrared first, which is the best bet, the possible bet to, figure out the compound. Next was supposed to be the carbon-13 spectrum, and lastly was the proton NMR. So, again, I want to repeat that. I want to apologize. The first that we're looking at is the infrared spectrum, the IR, the carbon-13, and lastly will be the proton NMR. Alright, so I'll be describing the carbon-13 NMR spectrum of the formula C10H12O. This contains several unique carbon environments, and we typically expect, 6 or 7 distinct carbon signals in the 13C NMR spectrum due to the symmetry and the equivalent groups. And so I'm gonna have to break this down, and, I'm gonna go ahead and elaborate on the carbon types and their chemical shifts. Alright, so let me go ahead and describe the chemical shifts for you all for the 13C NMR spectrum. The first one that I see here is the carbonyl carbon, which is the carbon double bond to oxygen. This carbon is part of a ketone group, appears downfield around 200 parts per million. It'll be around here. It has a downfield trend. And also, I want to clarify that it's very dishielded signal. It's typical for ketones, by the way. Very dishielded. Dishielded, sorry. Known for ketones. Right. So for the The second chemical shift that I see here, the major one, would be the aromatic carbons, the 6 carbon total. And you know, the phenol ring contributes 6 carbon signals, but due to the symmetry, you may see 4 distinct peaks. So the attachment for the carbon directly attached to the carbonyl is around 130 to 140, somewhere. Let me change colors so I can show you guys. This is carbon double bond to a carbon. And there's very broad ones as well. There's so for this one, the aromatic carbons, there are 4 distinct peaks. So I want to say the one that I focused on the most was 130 to 140, around there. There are other aromatic CH carbons, between 125 through 145. These carbons appear in around 125 to 145 range. The next one that I'm focusing on is the methane carbon, the CH. The central carbon of the isobutyl group, which is attached to the carbonyl and 2 methyl groups, show a signal around here, which I want to say it's around 35. This is 30 right here, so I would have to say it's around 35 aromatic carbon. Fix that. This is CH. All right. Lastly, last but not least, but the one that that came up to me was the methyl carbon CH3, the 2 equivalent methyl groups. Appears as a single signal, which is right around here. This big one right here. This is around 20. Has 2 equivalent methyl groups, appears single signal around 20. And they are in the same environment. And this one is the carbon attached to another carbon, which is aliphatic. But in summary, the 13C NMR typically shows the carbonyl peak around 200 parts per million. 130 through around 140, I want to say, was the one to carbon aromatic, and 30 to 40, which I came up with 35 because the aromatic carbon and the methane carbon is pointed through 35 and in between 40 and 30. And also, lastly, the carbon attached to another carbon, which is aliphatic. It's just a single signal, and it's right at 20. So I'm gonna go with 20 on the last one. I'll be describing the proton NMR spectrum, and the aromatic ring with the molecular formula of C10H12O. So let's break it down by the types of protons in the molecule and their expected signals. First thing I want to point out is these two. These two are around 7.2 or 7.2 to 7.9. So around 7 to 8 parts per million. Of course, parts per million. The phenol ring has 5 hydrogen atoms, which appears as a multiplet in the region. These signals result from the complex splitting between the aromatic protons and the integrating to 5 hydrogens total. Second would have to be the methine proton, CH and 1H. Should be this one. Let me change colors real quick so I can show you. It would be this one. And this one, it's attached to a carbon next to the carbonyl and the 2 methyl groups. The CH group shows up around, I want to say, 1 second here. Let me take a look at this. It shows up 3.4 to 3.6. Starts at 3.4 to 3.6. Also, of course, parts per million. And if we estimate it, we can estimate if it's 3.4, start at 3. And if it's 3.6, we'll end at 4. It appears as a septet or a multiplet due to the coupling with the 6 equivalent methyl protons nearby and the integrate for the 1 proton. Also, we expect the methyl proton CH3 6H, which would be, let me change colors here again, be this whole big one right here. And for this one, the 2 equivalent methyl groups attached to the methine carbon produces a double around 1.1, integrating to 6 protons. So this would be a equivalent to equivalent. Double it. And I want to see here. Okay. It's a bit difficult, but it's not that difficult. I know it's not at 1.5 and it's not at 1. I want to say here it's around 1.2 to 1.3. I'm going to stick to 1.3 parts per million. And its integration is 6 protons, and the doublet results from splitting by adjacent methine protons. And so each signal splitting pattern and integration match the structures, which at the end we need to confirm the arrangement of the protons in the phenol ring to see if this, if this compound has this type of proton NMR. And so I have my table over here. But last but not least, I want to show you guys that the degree of unsaturation, the sites of saturation can be calculated using the formula, which I also pointed it out here. The degree of unsaturation, as you can see, is the 2C carbon, 2 carbon plus 2 plus N, which is the nitrogen, number of nitrogen atoms, minus H, which is the hydrogen, number of hydrogen atoms, minus X. And as we know, the X is going to be 0, all divided by 2. So when we see that using the above formula, to calculate the degree of unsaturation, the degree of unsaturation equals to 2 carbon plus 2 plus nitrogen minus hydrogen minus X, which is 0 divided by 2. And I came up with 2 times 10 plus 2 plus 0 minus 12 minus 0, all divided by 2. So I got that, 5. So all in all, in summary, it will be 5 degree of unsaturation represented as an aromatic ring with 3 double bonds in one ring and 1 carbon double bonded to an oxygen bond outside of the ring. So the degree of unsaturation, as we found out, is 5. And the molecular formula that as we found out with all the spectrums, it comes out to be isobutyrophenone. Isobutyrophenone. And lastly, I also want to thank you all for watching.